sir. If you'd like to turn off the engine, please. The reason I've stopped you is that the speed limit on this road is restricted to 30 miles an hour. Your speed has been checked and found to be in excess of that limit. If you'd like to step out the car, please, sir. By exceeding the 30-mile-an-hour speed limit, sir, you have committed a moving traffic offence. I'm now going to require you to take a breath test. This is an electronic breath testing device. What I want you to do is to blow into the mouthpiece in one hard, long and continuous breath. That is fine, sir. As you can see, sir, the green light has stayed on, and that is a negative breath test.
The evidence from this machine isn't admissible in court, so had I failed here, I might have been confronted with a more formidable test. This is the machine you'd find at the police station that can accurately measure the alcohol content of your blood. Purely in the interest of science, I've had the odd glass of wine with my lunch, and we're going to find out just how much is in my bloodstream. Would you take me through the procedures if it would all been genuine and I'd been done?
Yes, indeed. Well, we start the machine off. It first of all wants to know who I am. It now wants to know my code.
Only an authorised police officer can perform the test, and all the information he enters into the machine is necessary to be certain that the printed output is acceptable as evidence in court.
First of all, it's purging out any contaminants that may be in the analysing compartment. And it will then check to make sure that the machine is recording 0. Then it will use the simulator over there to check its own calibration by taking vapour from a known quantity of alcohol. Now the machine has reported that that calibration is OK. It's now purging that out of the system. Right, I require you to blow into the mouthpiece in one long, hard and continuous breath until I tell you to stop. Stop. Thank you. The machine will now analyse that breath. It will report the result on the screen. It will clear itself and invite you to have another go. Right, there we are again.
The machine has to produce 2 consistent results, separated by another calibration check. Both these are taken after I've been under scrutiny for at least 20 minutes. If these were over the limit and I'd been driving, I'd be liable for prosecution.
And you can see that says 10. Well below the legal limit.
So, that's good news. I'd be allowed to go now, would
Yes,
I?
you would indeed.
Well, that's a relief. This is the printout from the intoximeter, and it shows I had 10 milligrams per centilitre, well under the count of 35. Thank goodness for that, or I'd have been in real trouble. Well, that machine really is very complex. It analyses the alcohol content of my breath, which is hard enough, but it can also separate out the acetones that my breath would contain, for example, if I were a diabetic. It has to be tamper-proof and produce evidence that will be acceptable in court. Well, the logic for that system is quite involved. We can understand the principles behind designing a complex system by looking at something a bit easier. This is a lift system that Steve lashed up this morning, and it really is quite nice. These buttons represent the buttons inside the lift, and there are sensors on each of the buttons. There are sensors on the buttons outside the lift to go up or to go down, or down from the top floor. And the doors have sensors to make certain that if something's in the way, the lift can't start off, it will actually open the door again. And there are even sensors inside the lift to make sure that it won't go down if it's actually overloaded. And there are quite a number of other sensors also controlling the system. It's all linked through into the microcomputer, and the conditions of what's happening are displayed on the screen. Well, it looks a very familiar system, John, but you need some very clear thinking to work out the logic of a system like this.
It does. The temptation is always to sit down at the computer and start writing some code straight away, but that's absolutely fatal. What you've got to try and do is to split the problem down into manageable subsections and then split it further down. And the type of thing you do is to write down on paper, in this style, a subsection. For example, if it's at the floor, then have an at-floor routine or procedure. Otherwise, have a between-floor procedure. So you split it down to 2 manageable bits. Let's have a look at this at-floor routine in more detail. Well, the at-floor routine would consist of checking sensors, opening and closing doors, and then deciding on the route that you're going to take, if you're going to take one at all. But notice that this isn't a formal basic or anything else. It's just an informal way of getting your ideas into order, and then you decide whether or not to move the lift. So you've begun to split the big problem down into a number of manageable subsections.
Well, at least it has logic to make sure the lift door doesn't open when there isn't a lift there to receive you. Well, there isn't one standard logic for running lifts, and we saw how many different approaches there can be to solving a problem at a robotics competition in Reading. The Army's Royal Electrical and Mechanical Engineers played host to the 1983 Build a Robot competition. 21 schools and colleges ended up in the finals. The brief was to design a robot which could locate a small cube placed several meters away, pick it up and carry it back across the baseline. Judges spent a whole day interrogating the robot builders.
The balance has to be over these two wheels.
There were various possible approaches to the problem, and as many solutions as there were competitors.
Well, it's efficient.
Is there a relay, 2 relays per motor?
Yes, we had because of the voltage. The voltage was too high, we had to put the transistor and the resistor in as a buffer, because these kept blowing.
And your final control system, you're coming through the ZX81, and you're going to program that through your tape recorder, right?
Yes.
You've not actually been able to have a program in EEPROM so that
No, time didn't allow it.
Yeah.
This entry from Ecclesfield School uses an onboard computer, which they designed and built themselves. The software was developed using a home micro. Like many of the competitors, they were able to find and pick up the cube, and they even anticipated that the course might be on a table and not on the floor, hence the procedure for reversing when it goes over the edge. Unfortunately, they hadn't worked out a satisfactory way of getting it back across the start line.
Look at that restraint.
Some had home micros on board. Caretaker Comprehensive Schools is searching from side to side for an infrared beam coming from under the cube, and it's hoping to trap the cube between its sticky antennae. An umbilical cord connected this entry to a domestic micro behind the baseline. It's using 2 optical detectors to locate a bright light, and optimistically, there's another light behind the baseline for the return journey. Hard luck, Royal Latin School. This is more like most people's idea of a robot. The Rednock School entry searches for the cube using stereo ultrasonics to home in on. The switches on the front tell it when it gets there and trigger the grab action. But the winner didn't use a computer at all. It was designed using hardwired logic, and this was the only software it needed. Well, a bit of lateral thinking there from the Hinchinbrook Comprehensive School. Many of those robots have dedicated micros on board which are programmed for one specific task, rather like having a computer in a washing machine that can only deal with the logic of doing your wash. John, how are those systems built and programmed?
Well, very often you use a computer development system. In fact, the software to drive this buggy used this computer as a development system. In other words, the software was actually written on this machine here, which was connected through the cord to control this through this computer to control the buggy.
That looks almost like a whole computer in itself, a replica of what's inside there.
Well, it is very nearly. And in fact, once you've designed and developed the software on this computer, it was actually downloaded into that one, which is in fact quite capable of running the buggy by itself. So after you finish the development process, if you'd like to unplug that, I think you'll find the buggy will keep running quite happily.
I think it'll actually work.
Because there is, as you say, virtually a complete computer. Well, I think you jogged it. It'll probably find its line.
It is.
There's virtually a complete computer on the buggy there.
And can we develop other systems on a micro as small as this?
It is difficult to develop systems on something as small as this because you really haven't got enough memory to use large development programs, and you haven't really got the ability to plug into lots of external input-output devices. But the memory problem you can get over fairly easily. This board here is called a second processor card, and it plugs into the computer. And it provides another microprocessor and a great deal more memory, in fact 64 kbytes of memory additionally. And with this unit plugged into the micro, you can start running large editors, large assembler programs, and other software tools needed during the development process.
So you can write all the software, but you still can't check it out because you need to have all the input-output devices, relays, analog to digital converters and so on. How do you do that?
Well, that becomes a bit messy, and if you start adding devices onto computers, you can end up with a lot of wires. So you tend to go for a separate development system. For example, a device like this, an open rack which contains a number of separate cards. This is one of the cards for this particular development system, and it's got 4 relays on it. Now, if during the development of your program you decide that you need some extra relays, all you have to do is to buy an extra card, plug that into the development system, and those extra facilities are easily made available. You don't have to get a soldering iron out. In a similar way, this board contains 4 high-speed analog to digital converters. So if you need those, plug them in. And yet another board in the development system is this one. This, in fact, contains an EEPROM, that's an erasable, programmable, read-only memory, which is a contradiction in terms. But the important point is that you can store a program in the EEPROM, and it'll stay there until such time as you consciously erase it. It doesn't just forget the data, the program in it, when you switch the power off. And to erase the EEPROM, you have, in fact, to stick it under a quite powerful ultraviolet light.
So the program would be developed in this system and then transferred and stored in that EEPROM?
Yes, and it would stay there typically for a week or so while you tested it in the field and so on. Very useful device.
It still seems a lot of equipment to me.
Yes, it is a lot of equipment, and clearly when you're moving to the final board for your washing machine, you want to take the minimal number of components that you need to build into the mass-produced product. More components are more cost in the end product. Typically, you would end up with a board like this. This consists of a central processing unit, but a rather special one, a CPU, a microprocessor, but it's one that contains also some read-only memory and some random access memory, some extra ROM and some RAM on that chip. It's a complete little computing unit. There is, in fact, on this board some extra memory and some connections to input-output devices off the board. So the whole of the development system was reduced to the essentials for one particular task.
But this can only do one thing. It's not general purpose in any way.
Indeed. Now, this particular board was used in this system over here. The problem was that you wanted to know how much power emerges from a ship's engine, so that you can adjust the speed of running of the engine and so on to reduce fuel consumption. The ship's motor engine is connected on that side of the shaft and the propeller on this side of the shaft. Here are sensors, torques, strain gauges to measure the torque coming down the shaft, and those are connected to the computer by connection through this coil, which actually sits over the shaft. And as well as that, we've got some a toothed wheel there, which is used to measure the speed of rotation of the shaft. So those those signals come into the computer, into this box, which contains that card, and there the torque, the speed, and the power of the engine are indicated.
So that the engineers can really optimise how fast they're using the engine to reduce their fuel consumption. Well, there may be dedicated micros in your washing machine, in your video recorder, or even in your camera. But I'm often asked how a micro can be used to control other day-to-day activities throughout the home. Switch heating on.
Heating on.
Being able to switch your heating on when you're a couple of hours away from home has several clear advantages. Switch heating off. And also being able to switch it off if you've forgotten it when you've gone away on holiday. At the other end of this wire is a voice recognition unit connected to a microcomputer that can recognise my commands and switch the central heating unit on and off. It's just one of a number of things which Paul Bond, a system designer in Cambridge, has put together for our benefit to show what can be done in the way of home security and control using a micro. He's used his own house and has basically made use of the wires that are already there, the existing ring main. Once the computer had let me in, I asked Paul how it's possible to use the ring main to control things like the front door lock.
Well, to control appliances in a house, we need a way of controlling devices and a way for the devices to actually know that they're being controlled. And the way we do that is to use a module rather like this. Plugs into the ring main, and the appliance itself plugs into this module. The module, to distinguish it from other appliances in the system, has a number which can be coded by a little code wheel on the back. And this device happens to have address number 6. So we can take, for example, this lamp. Standard lamp, plug it into the module, plug it into the mains. That module will be known as F6, so it will not recognise any commands that are not due for F6. And we can turn the lamp on and off by pressing the button. So we always have manual control. We can always override the control system. But of course, what happens if we want to control it somewhere else in the house where we can't reach it? We need a way of commanding it to do things. And to do that, we can use commercially available device to control those modules. And this is something that also plugs into the mains, so we can, for example, turn the module by selecting 6 on or off.
Now, this could be anywhere in the house at all.
This could be anywhere where there's a main socket.
How many devices can that control?
This can control up to 16 devices.
16. So what happened when I phoned up to switch on your central heating?
Well, of course, when you phoned in, we couldn't use a manual device like this. We need some form of automatic control. And the way we get the automatic control is by using a microcomputer. So we have a home computer with some ways of receiving commands from the outside world. Here's the equipment that we use. We have a system that can recognise the words that you're saying and translate them into numbers. The numbers then go into the computer, and then the computer can then decide to control devices itself. So, for example, the computer, via the mains control, would send a signal all around the ring main to the device that we actually wanted to control. So, for example, in this case, we could control a garage door, and we could either open the garage door or close the garage door. Although, of course, why anybody would want to phone up and actually control the garage door was another question entirely. The key thing is that you've got a computer at the centre of the control. It takes various ways of controlling devices. For example, I've been using a standard television remote control to control the pictures that we're seeing. And that's received through the television, goes into the computer, and as a result, we can control things via our standard TV remote control.
To do that, you need a special interface into the computer.
We need a special interface to do that, that's right. In addition, we can get information back through the ring main into the computer. And, for example, we could display that on our television.
Apart from switching things on and off, what else can the system do?
Well, we have quite a few things installed in the house at the moment, and this little diagram of a house that we've got should help to illustrate the functions involved. So, for example, in the area of control, what we can do is open the front door, or open the garage door, or turn an alarm on and off, which we might want to do independently. We can also turn on and off our central heating, or turn on and off the water boiler to affect control of our surroundings. On the sensing side, what we can do is we can detect whether one of our windows has been opened, or detect the presence of somebody on the stairs by virtue of fitting a pressure pad there, so that when they step on the pressure pad, it informs the system that a person is there. We have a movement detector installed in the hallway that can detect the movement of people, and that also can be linked to the alarm. And we also have built in a smoke detector, such that it automatically triggers the alarm independently of the computer system. So if the computer system breaks down, the smoke alarm still works. But also it will inform the computer so that the computer can phone you to inform you that perhaps a disaster is befalling your house.
So, as I could phone you up and turn your heating on if I knew the appropriate codes and passwords, you could actually control all this from a telephone in your own home, could you?
That's right, that's right. And you can use the fact that the system can be geared to only recognise one person's voice. So you need not be worried, for example, or I need not be worried that you phone at my house and control my house without my permission.
Can we see you do that?
Yes, certainly. Here we have a standard BT-approved cordless telephone, and we'll use it, say, to turn on this light. So, please turn on the computer light.
Lamp on.
And there we are.
Worked.
Or, in fact, we can open the garage door. Please open the garage door.
Garage open.
And there we are.
It seems like an awful lot of effort to go through to have to phone up to switch your lights on. What sort of real practical applications could it be used for?
Well, I think there are three areas we ought to look at it from. There's the point of view of controlling things. There's the point of view of surveillance, i.e. sensing the state of things without having to actually go there to look at them. And there's the point of view of security. So let's take each of those in turn. From the point of view of control, it can be very useful to control things in other rooms. So, for example, if one's ill and one knows somebody is calling at the front door and who they are, it's useful to be able to open the front door. Or, for example, if one happens to be disabled, it's quite useful to use a headphone set like this that you can wear that leaves your hands free to do other things.
And you can switch on your television
And you can switch
set.
on your television set, or switch on and off lights.
Channels.
Or even change channels on your television, all using the control aspects of the system. Then the surveillance. Is my front door closed? Is my garage door closed? Are all my windows closed? Have they been opened at all? Because then one can go and check that they're firmly secure. So from the surveillance point of view, it gives you peace of mind. On the security side, I think it should be stressed that you pay for what you get in security, and this system shouldn't really be treated as a serious home security system. I think if somebody really wants their home to be secure, they ought to seek professional advice.
You have to be very careful connecting your computer to the mains this way. Can it be dangerous?
Oh, yes, indeed. It takes a lot of experience, knowledge, and the right equipment to develop an interface like that. And it can't be stressed enough that people with home computers shouldn't play about with making their own interfaces. Mains can kill even the most experienced people.
That interface is not available on the market yet.
That's correct. That interface isn't available on the market yet. Though, I suppose if enough people wanted it, then somebody somewhere would make one.
Thank you, Paul. There'll be more on voice recognition next time, and we're looking at more advanced computerised robotic systems. Till then, goodbye.